We're back for yet another totally enjoyable lecture on word problems. This is a classic example of a mixture problem. But before we get started, I wonder if you can tell me where satisfaction comes from. Well, it comes from a satisfactory, of course. See, it's getting a little bit later, the jokes are getting a little bit worse. I've gone ahead and already written up our chart here. We're going to have orange drink, lemon lime drink, and a mix. We have the number of bottles, we have the price per bottle, and we also have the total cost of these. So let's go ahead and look at page 66, example number 3. Two types of soft drinks are mixed together to make a fruit punch. Orange drink sells for 89 cents for a 2-liter bottle, and lemon lime drink sells for $1.19 for a 2-liter bottle. How many 2-liter bottles must be mixed, of each must be mixed to produce 30 liters of fruit punch that sells for $1.09, a 2-liter bottle? Well, first off, let's see what we're going to do. We've been given the price per bottle for orange drink, for lemon lime drink, and for the fruit punch mix. So let's go ahead and fill those values in. Okay, the price per bottle of orange is 89 cents, but I'm just going to go ahead and write it as a whole number. Let's see what happens. For lemon lime is $1.19, I believe, and the fruit punch is going to be $1.09. Now, let's see what we want to find out. This says, how many 2-liter bottles? So we're buying these in 2-liter bottles. How many bottles of orange? How many bottles of lemon lime are we going to have to mix together to make 30 liters of the mix? Once again, back to the chemistry, units are important. The bottles come in 2 liters. We're using just like a 2-liter Coke bottle. But we want to be able to have 30 liters of our final mix. So how many 2-liter bottles are we going to have? It's not going to be X bottles of orange, 30 minus X bottles of lemon lime, because our units, if you will, are different. Our bottle sizes are different. The sizes of the unmixed drink come in 2-liter bottles. The sizes of our fruit punch is going to be in 1 liter. And yes, that's exactly what it is. If we need to have 30 liters and yet we have 2-liter bottles, we're going to have some unknown number of bottles of orange drink, and we're going to have the total number of bottles, total number of 2-liter bottles that will give us 30 liters of mix would be 15. So if we say 15 minus however many bottles of orange we have, that has to be the total amount of lemon lime that we have. And how many total bottles of mix are we going to have here? Let's think carefully about that. We're going to have 30 bottles, so you're going to have 30 liters that we're measuring, but it's still just 15 bottles. 15 2-liter bottles is going to give us a total quantity of fruit punch that's 30 liters. The number of bottles times the price per bottle is going to give us our total cost. And I have been doing this all night, not having my calculator handy. Okay, 15 times 109, 15 times 109 is 1635. If I put everything, ignoring the decimal points, then you can add the decimal points at the end. If you're not comfortable with that, go ahead and make this 0.89, $16.35, $1.09, whatever you're most comfortable with. And then what is our price going to be here and here? Well, yeah, it's going to be 89x, and then it's going to be, whoops, I should put the x in, and then it's going to be 119 times the quantity, 15 minus x. And we now have our chart all filled in, so what can we do together? Do we know what the total price is going to be? Yeah, as a matter of fact we do. because we know the price per bottle of our mix is going to be $1.09, we know we're going to have 15 bottles, so we know that our total price is going to be $16.35. So the cost of the orange, which is 89x, plus the cost of the lemon lime, let me move this over again here. Cost of the orange is 89x, plus the cost of the lemon lime is 119 times the quantity 15 minus x, is going to give us our total cost, which is 1,635. We're going to carry out our distribution. See here where I have 15 minus 5, obviously that's not what that's supposed to be. It should be 15 minus x. So we now have 89x plus 119 times 15. This is my very favorite calculator. I've had it for almost my entire married life, and I've been married 26 years. Has a nice feel to it. It clicks, and I know when it's working. It has all the scientific stuff on it that I need. 119 times 15 is 1785. 1785 minus 119x is equal to 1635. Combining like terms, and we're going to end up with negative x again. We have 119 minus 89 is a negative 30x is equal to 1635 minus 1785. That should be like a negative $1.50 or something. I'm not liking how this is looking. 1635. Yes, it is. 1635 minus 1785. The number was getting lower than the cost per bottle should have been, but we're not looking for the cost per bottle, are we? We're looking for the number of bottles. So we're coming right into where it needs to be. Is equal to a negative 150. Negative 30x is equal to a negative 50. So x is equal to 5. 15 minus x is equal to 10. So we're going to have 5 bottles of orange soda at 89 cents, and we're going to have 10 bottles of lemon lime soda at $1.19. When we mix those together, we're going to end up with 15 bottles of punch that we can sell for $1.09. You can go back through and track these. I haven't labeled the prices down here. To finish your problem, you would say that you would have 5 bottles of orange soda, and then you would have 10 bottles of the lemon lime soda. And that's a pretty basic, very straightforward example of what a mixture problem would be. Let me see if I want to go ahead and do number 14. Okay, let me go ahead and do number 14. See if I can save my chart that I already have written up here. And actually it's just as quick to rewrite it. We're dealing with chemicals. How perfect for all of you kids who are taking chemistry with me. And here we're going to set up a similar chart. We have 3 lines in there, and we have this here. 1, 2, 3. Now, let's go ahead and read our text, see what a problem is. This says example 4 on page 67. Says a chemist has a solution that is 3% alcohol in water and another solution that is 8% alcohol. How many kilograms of each should he mix to make 15 kilograms of a 5% alcohol solution? So what are we having? Well, we have two solutions that are given to us that have differing concentrations. One is 3% alcohol and one is 8% alcohol. So we have the 3% alcohol and we have the 8% alcohol. And we want to go ahead and figure out what the correct proportion is in which we can mix these two alcohol solutions so that we end up with a new mixture of 5% alcohol. So our new mixture is going to be 5%. And there you have 5%. Now let's look and see what information we have. Well, this says that we have how many kilograms of each solution. So we want to find out the total number of kilograms of solution, that when we mix so many kilograms of solution A, so many kilograms of solution B, that we end up with 12 kilograms of our new mixture. And 12 kilograms of solution is going to be about 25 pounds. Now, what else do we have? Well, how about if we put the percentage of alcohol and the kilograms of alcohol? Let's see what happens. Percentage alcohol and the kilograms of alcohol. If we want to have 12 kilograms altogether of our mixture, let me finish this column right here. Let's just say that we have X of 3% alcohol and 12 minus X of the 8% alcohol, because it doesn't matter if we don't know how much of either solution we have. We know that the total amount of the new mixture we have is 12 kilograms. And since they are coming only from two different solutions, 12 minus whatever this first solution is, whatever that first quantity is, 12 minus X, has to be the amount of one solution, while X is the amount of the first solution. Now, if we have 3% alcohol, well, what percent is that? Well, let me see. It should be 0.175, right? No. 3% is 0.03. 3%. 0.8%, 0.08. 0.5% is 0.05. Now, if we know the kilograms of solution, we know the percentage of alcohol. How do we calculate the kilograms of alcohol that there are of each of these three separate concentrations? I think it's raining again. Well, that's easy. 0.03% times a kilogram. 0.03x, 0.03x, 0.08x. And then we have, is that right? 0.08x, 0.03 times x, 0.08 times x? No. 0.08 times the quantity 12 minus x. Because we're saying, for the purposes of this problem, let's define our x variable to be the number of kilograms of the 3% alcohol solution that we're using. When we define it that way, the number of kilograms that we have of the 8% alcohol solution has to be our total number of kilograms of the new solution, which is 12, minus the amount of the 3% alcohol solution we have, which is x. So the kilograms of alcohol that we have in our 8% alcohol solution has to be 0.08 times the quantity 12 minus x. And then kilograms of alcohol in our 5% solution is an easy one. 0.05 times 12, that's 60. We're going to move the decimal point 2 units. And we have 0.6 kilograms, or 0.6, just so that we're real clear with what we're doing. Now we have our chart filled out. A come up with our variables, come up with the relationships between the two known concentrations of alcohol in solution that we have. Now we've got to figure out how much of each we need so that when we mix those two solutions together, that mad scientist pours those two together, we end up with what we want and not something really strange. Well, shouldn't it be true that if this is a mixture, and we're going to take beaker A and beaker B, and we're going to combine them, there's just a little bit in here and there's some in here, and we combine them together, that would be the amount of alcohol that's in here, plus the amount of alcohol that's in here, all is now in this same glass. So this is all going to be at 0.6 kilograms of alcohol. So the amount of 3% alcohol solution, the amount of 8% alcohol solution combines to give me the total amount of solution at 5%. So the amount of 3%, 0.03x, plus the amount of 8%, 0.08 times the quantity 12 minus x, is equal to our total amount of alcohol contained in that final 12 kilograms of solution. Let's go ahead and multiply the equation through by 100. 3x plus 8 times 12 times the quantity 12 minus x is equal to 60. Make sure that when you're multiplying by a factor of 10 that you move the decimal point the correct number of places to the right or to the left. Now we have 3x plus 2 8s are 96 minus 8x is equal to 60. We have negative 5x. Let me check and see. Okay. Negative 5x is equal to a negative 36. We subtracted the 96 from the 60 over here on the right-hand side of the equation. And we remember to write negative 5x. Divide both sides of the equation by a negative 5, which tells me that x is equal to 36/5 of a kilogram of 3% alcohol. Now, that's not really going to work very well for what we need. Because we're not going to want to mix fractions here with the kilogram. This is something that we've been learning in chemistry, even though for the purposes just of algebra, 36/5 would be a nice number. We're going to go ahead and convert that into a decimal number because that's what scientists like to work with. So 36 divided by 5 is going to give us a value of 7.2. What is x? X is the number of kilograms of the first solution. So 7.2 kilograms of 3% solution. 12 minus x, or 12 minus 7.2, is going to give us 7.8 kilograms of the 8% alcohol solution. You see, there's not really a whole lot of difference. You're just adding, for us, a little bit more than a pound of the 8% solution to balance it down to 5. But that's because there's a whole lot more alcohol in 8% solution. There's 2.5 times as much alcohol as there is in this. So that's why these quantities are so similar. And that's all the problems that I'm going to do for section 2.6. Go ahead and do the best job that you can. Let's come back and finish just a few more graphs, and then we'll go ahead and take our test for chapter 2. and I will see you shortly.